I'm Jasmine, and I'm going to be teaching you how to do 2010 Bc Frq number 6, or the Taylor series problem. Before we start, I think it's important to note that this is question 6, which means calculators aren't allowed. So put your graphing calculators away. Let's start with part A. The function f defined above has derivatives of all orders. Let g be the function defined by g of x equals 1 plus the integral from 0 to x f of t dt. Part A says, write the first three non-zero terms and the general term of the Taylor series for cosine x about x equals 0. Use this series to write the first three non-zero terms and the general term of the Taylor series for f about x equals 0. Okay, so let's start. We know that cosine x can be represented as the summation from n equals 0 to infinity of negative 1 to n x to the 2n over 2n factorial. And the question asked us to represent this series as three non-zero terms as well as the general term. So let's write again. Cosine x is equal to, plug in 0, we get 1. Plug in 1, we get x squared over 2. Then we plug in 2, we get x to the 4th plus x to the 4th over 4 factorial. And then, again, we know the general term, so it'll be dot, 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 plus negative 1 to the n, x to the 2n, over 2n factorial. The next part of the question asks us to use this summation and the general terms right here to write the first three non-zero terms and the general term of the Taylor series for f about x equals 0. And so this definition says that for x equals 0, f of x is equal to negative 1/2. So we know that f of x will be negative 1/2. And then we use the cosine x minus 1 over x squared for x not being equal to 0 to find out the rest of it. So it's plus x squared over 4 factorial. And then it's plus x to the 4th over 6 factorial. And so if you look at this, it's very easy to find out the general term. So you're going to add, it's negative 1, but since we started with a negative term, it has to be n plus 1. This is still x to the 2n, but instead of being over 2n factorial, it's 2n plus 2 factorial, just to account for the x squared that's defined in the function. Okay, let's start part B. Use the Taylor series for f about x equals 0 found in part A to determine whether f has a relative maximum, relative minimum, or neither at x equals 0. Give a reason for your answer. So f prime of x is equal to 2x over 4 factorial plus 4x cubed over 6 factorial out of the terms that we know right now. We could do the general term, but not at the moment. And so if you plug in f prime of 0, you're going to get 0, which means that we can't use the first derivative test. So let's instead use the second derivative test. So we know that f double prime of x is equal to 2 over 4 factorial plus 12x squared over 6 factorial. So if we plug in 0 again, so f double prime of 0, we get 2 over 4 factorial, or 1/12. Based off of our answer, we know that by the second derivative test, f has a relative minimum at x equals 0. And so you should actually write this because this is not enough math. So you really need to put in a conclusive statement. So we'll write, because of the second derivative test, f of x has a relative minimum at x equals 0. Okay, let's go to part C. Part C says to write the fifth degree Taylor polynomial for g about x equals 0. So we know that g of x is equal to 1 plus the integral from 0 to x f of t dt. So the easiest way for me to think about this problem is that g prime of x is equal to f of x. So if we write this down, we'll get negative 1/2 plus x squared over 4 factorial minus x to the 4th over 6 factorial. And then to get back to g of x, we take the integral. So it's negative x over 2 plus x cubed over 3 times 4 factorial minus x to the 5th over 5 times 6 factorial. And then, of course, we have to remember this adding 1 in the beginning. And so g of x, the fifth degree polynomial, is equal to 1 minus x over 2 plus x to the 3rd over 3 times 4 factorial minus x to the 5th over 5 times 6 factorial. Okay, part D says the Taylor series for g about x equals 0 evaluated at x equals 1 is an alternating series with individual terms that decrease in absolute value to 0. Use the third degree Taylor polynomial for g about x equals 0 to estimate the value of g of 1. Explain why this estimate differs from the actual value of g of 1 by less than 1 over 6 factorial. So given this, we know that g of 1, and they only want us using the third power, so we're going to just forget about this for now. So it's equal to 1 minus 1/2 plus 1 over 3 times 4 factorial. And so when you add and subtract these fractions together, you're going to get 37 over 72. And so since the Taylor series for g is alternating, we can use the AST error. So it's the absolute value of g of 1 minus 37 over 72 is less than 1 over 5 times 6 factorial, because remember, we're using this part of the polynomial, and that is definitely less than 1 over 6 factorial. So we have just proved this. And again, it might be helpful if you write that since this is a decreasing function, this is a decreasing and alternating function, we know this to be true. So the last thing before we go is that I just want to go over the scoring and how everything works. So for part A of the problem, it's worth 3 points. One term is for getting cosine x correctly. The second point is for having the first 3 terms of f of x, and then the last point is for having the general term. For part B, there are 2 points. So the first point is determining that f prime of 0 is equal to 0. And the second point is to answer with a reason. And so we answered with both math and with a sentence. And then part C is 2 points. The first point is that you have 2 correct terms, so 1 minus x over 2. And the second point is for the remaining terms. And then part D, there's 2 points again. One is that you have the estimate, and the second point is for the explanation. And I hope that this was a very informative video. If you'd like more practice with problems like these, you can go to the Bc Frq 2011 number 6, 2012 number 6, 2013 number 6, 2014 number 6, 2015 number 6, and 2016 number 6. Thanks for watching.